Let's resume. So we've spent the first 5 chapters of Rudin basically building up a lot of machinery. We've built up machinery that allows us to think about the real numbers carefully. We also built up machinery that helped us think about functions carefully, what it means for a function to be continuous, what it means for a function to be differentiable. What I want to do with the remainder of this lecture is sort of point towards some ideas that you're going to encounter if you take analysis 2. And that is, one of the big ideas is, it's not just the real numbers or Rn that we're interested in. You know, we built up all this machinery about metric spaces. What's it useful for? Okay. So one of the big places where it's used is thinking about functions as living as a metric space living in their own metric space. And so I want to talk about sequences of functions. And this is actually one of the main motivations of analysis. So we've said what it means for points to converge, but what does it mean for a sequence of functions to converge? So for instance, I might have a sequence f1 of x, f2 of x, etc., f3 of x. What does it mean for a sequence of functions to converge? So here I'm thinking about the functions as real-valued functions. But what would you say it means for a sequence of functions to converge? Like, maybe I have functions like this and rather boring example. What would it mean for this sequence of functions to converge? What would you give me a notion of convergence here? Katie?
Keep getting closer to one specific function, so the values for each point go closer to a single point.
Okay. So for instance, take some points here, fix a point that you're looking at, and see if they converge to something. Is that sort of what you're saying? Right? Okay, good. And do that for each one of these. Right? And then I'll have some limiting function, perhaps, that this creates. Yes? Okay. Yeah, so one way to answer this question is pointwise convergence. This is what we call pointwise convergence. Basically, fix x, and then ask yourself, does fn at x as a sequence now evaluated at a particular point converge? If it does, we say it converges pointwise, and we give it a name. We say it has a pointwise limit, which is just what you think it is, namely f of x is the limit of fn at x as n goes to infinity. That is a sequence of numbers after all, right? So I'm calling this limiting function f. If this limit exists for every x. Okay? Okay, let's explore this idea. Tell me what the pointwise limit of this sequence is. Example 1. How about, can't even draw these. Here's a sequence of functions, and here the functions are fn at x is x divided by n. Does this converge pointwise? To what? To the 0 function. This is the function 0, right? In fact, I'll write this like this, f of x equals 0. Yes? Okay, very good. Pointwise. Okay, we'll come back to that example. What about this function? How about f sub n of x equals x to the n, and we're now limiting ourselves to the domain 0, 1, not the whole real line. Does this converge pointwise? Let's see. What is f1? X, yeah? Yes? What's f2? X squared. What's f3? X cubed. What's f4? X to the fourth, etc. Does this converge pointwise? Yeah? To what? Zero? What about at 1? It stays at 1 for 1, and everywhere else? 0. Ooh, interesting. So it converges pointwise. Yes, but to the function f of x equals 1 at x, if x equals 1, and 0 else. On 0, 1 only. Okay? Interesting. Let's look at another example. How about example 3? What if I have this function? This is the function that has got a spike. And the spike is at height 1, and it's supported on n minus 1 and an n plus 1. So the spike is at n, and it lives between the next two integers. So f1 is over here, f2 is over here, f3 is over here, f4 is over here, etc. Okay? So help. What does fn converge to? Does it? What does it converge to? Pointwise, if I look at a particular, let's look at pi. What is it doing? It's 0, 0, something, 0, something, 0, 0, 0, 0, 0. Would you agree? Pointwise, all these things converge to what? Good. Interesting. Interesting notion of convergence. Is it the right notion? Is it the best notion of convergence? What if I look at this function? How about f sub n at x is 1 over n sine n squared x? Okay, what's that doing? Well, okay. I'm just going to roughly draw something. Here's the first one, yeah? The second one has what amplitude? Smaller, right? And then what frequency? Bigger, yeah? Okay, so it might do something like this. And then the next one, even more frequency, like this. What does this converge to? Yes, you're right, also the 0 function. Don't be fooled, not all sequences of functions converge to 0. It just was easier examples to construct, obviously. Okay. But what can you learn from these examples? This sort of points out some very, very interesting behavior. Well, I mean, here's the kind of question we've been dealing with. When you have sequences, what properties are preserved by the limiting operation for functions? What properties are preserved by limits? By pointwise limits. I mean, for instance, is it true that the pointwise limit of a continuous function is continuous? No. Why? See example 2. Oh, okay. What about what about derivatives? If I take the derivative of a limit, is the limit of the derivatives? And a very good example of this is in physics, where you have an infinite sum and you're asked to take the derivative of an infinite sum and you do it term by term. Wouldn't you agree an infinite sum is like a limit? Okay.